So a conformer is an isomer. Specifically, it's the isomer that exists in a new conformation. It's related to each other as a new conformation. Conformers, conformational isomers. What about the amino acid that I had you guys do on the worksheet from last class? How many conformers did that amino acid have? How many did I give you a template for? 6. So is it every molecule has 6 conformers, or some have more, some have less? What do you think? Well, since we're, sorry, that one for you. Since we're typically drawing these Newman projections for, what am I saying? Since we're typically drawing these Newman projections for like a carbon-carbon single bond, we're looking down a carbon-carbon single bond, then there's usually the same number of groups. 3 on the front carbon, 3 on the back carbon, and we look through the carbon-carbon bond. Does that make sense? I mean, you can have a Newman projection of sp2 hybridized carbons, in which case there's only 2 groups on the front, 2 groups on the back, but typically it's sp3 hybridized carbons. So maybe it doesn't depend on the number of bonds, since the number of bonds is the same. And since the same number of bonds exists, then it's the same number of isomers, conformational isomers. There's 6 conformers of every molecule. Some might be identical in energy. But if we labeled all of the atoms on the front carbon and the back carbon, then we should have a conformation where we see, let's say, group 1 on the front eclipsed with group 1 on the back. Group 1 on the front eclipsed with group 2 on the back. Oh, here you go. No, that's okay. I just paper clipped them for you. Group 1 with group 1, group 1 with group 2, group 1 with group 3. So we should have 3 eclipsed conformations, at least, right? Group 1 eclipsed, group 1 with group 2 eclipsed, group 1 with group 3 eclipsed. And then we have 3 staggered conformations everywhere in between those eclipsed conformations. So all of these Newman projections should have a total of 6 conformers possible. A molecule that, when you consider rotating around a single bond, should be able to give you 6 conformational isomers. So the answer here, how many conformers? It has 6. If we were asked to draw the highest energy and the lowest energy, then we should draw one that is eclipsed and one that is staggered. We know that the highest will be eclipsed. We know that the lowest will be staggered. The highest energy eclipsed, how should I arrange all of these groups? Put the biggest groups eclipsed with each other. Larger groups, larger strain. So that means the highest energy conformation, nobody named this. Come on, Britton. Not quite. It's a good start. I need locants. 1,2-dibromoethane, which is a structural isomer from 1,1-dibromoethane. So it's useful to actually know that 1,2-dibromoethane is what we have and not 1,1-dibromoethane. Tell me, how is it 1,2? 1,2-dibromoethane. What does ethane tell us? 2-carbon alkane. Where are those 2 carbons? And where are the bromines coming off? One comes off of carbon 1, one comes off of carbon 2. 1 bromo, 2 bromo. But of course, we don't separate them.
And so I was thinking it was like a 4-carbon chain.
Easy mistake to look at that zigzag and see it as a butane chain. Good. I'm glad you brought it up. 1,2-dibromoethane. You would have said 1,4-dibromobutane is what you were going for. Good. Okay. So our highest energy conformation, the bromines should be eclipsed with each other. Doesn't matter really where we put them. Top, bottom left, bottom right, they should just be eclipsed. We've got an eclipsed steric strain in addition to all the torsional strain. This is going to be my lowest energy. How should the bromines be arranged relative to each other? One across from the other. In other words, I don't want my bromines gauche to each other. I don't want to set them offset to one another. Instead, we can describe this relationship as being anti to one another. On the front carbon, it's straight up. On the back carbon, it's straight down. Those groups are anti. Well, I could have also drawn this anti-Newman projection where they weren't straight up and straight down, but they were up to the right and down to the left. That's still an anti-relationship because they are directly across from each other. The only difference here is that I've just taken the whole conformation and I've rotated the whole conformation by a little bit. And remember when we looked at wedged groups and dashed groups, and we said that something that's wedged always ends up on the right-hand side, and something that's dashed always ends up on the left-hand side. And so we can look at groups and say, if they're cis to each other, then they're both on the right, and if they're anti to each other, then they're across from one another. And we see that. A bromine to the right, a bromine to the left. One would be wedged, one would be dashed in the bond line structure because they're directly across from each other in the Newman projection. Okay, now let's get back into chairs because we left off right at the coolest part. This linear structure has 6 conformations. How many conformations does my cyclic structure have? 6? No. Because with my linear structure, I was able to freely rotate continuously around my sigma bonds. Not having a very good time freely rotating around my sigma bonds anymore. Dang, broke my molecule apart. I don't have the freedom of rotation in a ring that I have in a chain. So I have fewer chair conformations. I have only 2. 6 conformers, 2 chair conformations. Okay, I will admit there are more than 2 conformations for the ring. One is a very high energy boat conformation. And we call it boat because it really does look a bit like a boat. But that is a transition state, much like the eclipsed conformations for our linear chains. That's just a transition state. If a molecule can get to that energy in that conformation, then it will fall down to a lower energy conformation. And we're limited to 2 chairs. We could call this chair A and chair B. And we can have some equilibrium between them. If I'm drawing this with a y-axis of energy, would you agree that this says my 2 chairs are of equal energy? Did we find that was true of all of our staggered all of our other conformations, like staggered were all of equal energy, eclipsed were all of equal energy? No, we had some that were staggered, so on the lower half, but higher than one another or lower than one another. And that's true for chairs as well. Sometimes chairs are of equal energy to each other, and many times chairs are of opposite energies from each other, different energies from each other. We can have a high energy chair conformation and a low energy chair related to each other through a boat, but we're going to focus just on these chairs. And this process of taking one chair and showing it as another chair is called a chair flip or a ring flip. I say both because I kind of forget which one most people use, and it doesn't really matter. You are flipping the conformation of the ring. You're flipping the chair conformation. So this is where I left you last class. We said all of our red substituents, some are up, some are down, but they all can be described with what term? Axial. All of the red substituents are parallel to the axis of the ring. So we say all of these red substituents are axial. Now if I flip it into a high energy chair conformation, a high energy boat, there's my boat, and then I relax it down again into another chair, I have successfully flipped my chair. Look at my red substituents. Are they still axial? They are not. They're now described by what term? Equatorial. In a chair flip, equatorial groups become axial groups. Axial groups become equatorial groups. Now I want to point out how the terms up and down stay the same. Let's pay attention now to this yellow substituent. Is the yellow substituent up or down? Up. Is it axial or equatorial? Axial. So we can describe the yellow substituent as being up, axial. Let's go through a chair flip. I want you to notice, can we also describe the carbon the yellow group is attached to? Is it an up carbon or a down carbon? It's an up carbon. It lies higher than some of the others, and it has an axial group that points up, so we can describe this as an up carbon. In this chair flip, notice what happens to that same carbon. Is it still up? It's now a down carbon. Up carbons flip into down carbons flip into up carbons. What about the group? Is it still axial? It's now equatorial. Is it still up? It is. On this down carbon, the equatorial position is pointed slightly up relative to its neighbors, which point slightly down. So this is the pattern that we'll see in ring flips. If it's up, then it's up, then it's up, then it's stuck. It's an up substituent, whether it's axial or equatorial, and it will go through both conformations to be axial and equatorial, but it will never go from being up to being down, ever. So in a chair flip, we see up carbons go to down carbons and vice versa. We see axial groups become equatorial groups and vice versa. But we see up groups stay up. Down groups stay down. Okay. Here's what I wanted to. I know I ran out of sheets and I didn't bring extras. But we still had some space on the bottom of that form. Nope, that's not what I wanted. All right, so I want to take us on a process of taking a structure from a bond line, and we'll call this a top-down view. And let's just start with this compound. Can we call that methyl cyclohexane? Is that a good name? We can call it 1-methyl cyclohexane, but we don't need to. Is that methyl group up or down? Well, because it's wedged, that means it's coming at you. So when you flip this molecule onto its side, something that's coming at you will be up. So something wedged, up. Something dashed, like the hydrogen on the other side of the carbon, this we'll call down. And then we get 2 chair conformations. Why? Because every 6-membered ring has 2 chair conformations. So let's analyze both. That carbon is going to be on, that methyl group is going to be on one of these carbons. Doesn't really matter where. By the way, this is a good place for you to fill this in on the bottom, where you already have some templates of chairs. So let's pick a spot. To be quite honest, I like these 4 positions the best. The corners. I don't like these middle positions. The reason is drawing the perspective of the axial and equatorial groups in the middle is really challenging, but drawing the orientation of axial and equatorial groups on the corners is very easy. So let's pick this back carbon on the back right, and that's where I'll put my methyl. Is this an up carbon or a down carbon? It's an up carbon, as is this and this carbon. I've got 3 up carbons. These are all up. What are the 2 positions on an up carbon? Up axial and down equatorial. So I'm going to sketch those in. Here's up axial, comes straight up out of that up carbon. And here's my down equatorial. I've got a CH3 that is up. So it goes into the up axial position. The hydrogen shows up in the down equatorial position. Now let's do a chair flip. So that up carbon needs to become a down carbon. Boy, this is going to give me a seizure. Which down carbon would you like? There are 3 of them. It doesn't matter which one. So long as you pick, that's enough. So long as you pick a down carbon. Just needs to flip. Let's do this corner, because I don't really like the down carbon to the left because it's in the middle and it's harder to show the perspective there. So I'm going to pick this down carbon in the corner. Down carbon has 2 positions, down axial and up equatorial. Where is the methyl? If it's up, then it's up, then it's up, then it's stuck. And methyl is up. So methyl goes up. It's stuck there. It cannot change that relative orientation. And what goes down? The hydrogen. Now, Camilla, I want to come back to that point because this is very common. It's very easy to think during that ring flip, whatever is straight up is going to totally transition to become straight down, go to its opposite. But that's not how the groups are able to move. These groups are limited in their rotation. They can either rotate slightly up or slightly down. They're unable to do this full twist. You can see what's happening to my ring when I try to do that. I can't get that yellow group to be straight down, down axial. I can only get it to be equatorial and still stay up.
So when you say we can choose any down carbon to put it on, are we just assuming that, we're drawing it in the right equatorial / axial position, and then we're just like switching, like turning our ring?
Yes, yes. So I drew it like this, yeah? Here's my up equatorial methyl, but I could have also drawn it like this or like this, and it would have stayed up equatorial, but it just would have been on this carbon or that carbon instead.
Is there any time where we need to worry about that rotation?
No. In fact, one thing that's harder for me as the grader, well, I actually stopped having my students draw chairs because you guys kind of are not good at it, and I stopped trying to make you good at it. And I'm not going to have you draw chairs on exams. I'm going to have you analyze chairs on exams. So I'm going to have you draw less chairs. But you could draw a chair any way that you want to. It's my job as the grader to be able to interpret whether it's drawn correctly or not. There are easier ways for me to interpret that, but there's a lot of right ways for me to interpret that. In fact, this molecule can also be flipped like a pancake, and now it's drawn like this. Because I flipped it over. This is similar to what you guys were doing last week. As I flip it, my group starts to look like it's down now. Doesn't matter. Doesn't matter that it's down. That's okay. Now it just stays down. Oh, I want to draw this, but have it down. I'll just take this chair and flip it over, and now it is down axial. I want to have this, but have it be down equatorial. I just take my chair and flip it over, and now it is down equatorial. It's the same molecule, new perspective. Same conformation, new perspective. Here's the real question. Are these chairs equal energy, or are these chairs of different energy? Equal, different? Do you guys want to rationalize? These two? Oh, yes. Good point. If I flipped this over, same conformation, different perspective, same energy. Between them. Different energies. Hamza, do you want to try and say why?
I think because it's got fluid carbons, like from top to bottom.
Could you tell me which one is higher energy?
I think the one on the right, because since the methyl group on top, it will interact with the other hydrogen, and that's something called
You did your reading.
I did.
Diaxial strain.
Exactly.
So you're thinking it's this one that has the diaxial strain? Or did you say this one? Oh, the one on the left. Good. The best way to figure out whether the axial or equatorial group causes more strain is to do a Newman projection onto your ring. But if you try to do a Newman projection down one carbon-carbon bond, then you will be doing a symmetry on another carbon-carbon bond, and it's going to look like a double Newman projection. And do you see that that's what you have on the far right side? A double Newman projection. So since Hamza said he thinks this is higher energy, let's look at this. And let's set our perspective down these carbon-carbon bonds. The methyl group will be on the back carbon of the right Newman projection. So that back carbon has a methyl group that comes straight up, and it has a hydrogen that is down equatorial. You know what? I didn't check. Did I? It doesn't match the template that you have. Dang. It's just upside down. Do you know what? We can take the perspective backwards, and then it will work. Okay, but if we take the perspective backwards, That means I have to go behind the board to look at it. So where is the methyl? It's on my left-hand carbon. Oh. Flip what? Yeah, do whatever you need to do. So let's, or you can modify what you have or redraw another Newman projection adjacent to it. I think this is what I want to keep. Methyl group is coming straight up. What about that other bond? What about that third bond on the back carbon? It's also technically like down axial or down equatorial. I've got up, down to the right. I should have down to the left. Well, that would make that a down carbon. Is this a down carbon? Yeah, it is. And that down carbon actually connects to the other Newman projection on the back exactly as I'd want it to, because this is an up carbon with an up hydrogen and a down equatorial hydrogen. On the right front Newman projection, I have a front carbon that has a down axial hydrogen. It's a down carbon. And an up equatorial hydrogen. And my Newman projection reflects that. The third group off that front carbon, it's an up carbon. And now my up carbon connects to the other side as well. Do we see torsional strain in this Newman projection? Salem, do you want to try and define what torsional strain is or how we identify it?
All I can think of is the
Sorry.
That's all I can
But that means the twisting, right?
Yeah.
So what happened as a result of the twisting was that our bonds became eclipsed and the electron pairs repelled each other. So torsional strain is that electron pair repulsion. Do I have electron pairs eclipsed with each other? No. This is a staggered conformation. Chairs are staggered conformations. So I don't have torsional strain. Do I have any steric strain? Jordan, you want to try and point out where the steric strain is?
With the carbon and the CH3.
The up carbon.
Yeah, the up carbon, because none of the hydrogens qualify for.
Good. None of the hydrogens will qualify for strain. We won't identify it there. But this CH2 is gauche to the CH3. This is what Hamza brought up earlier. And remember what this carbon was? It's just a different up carbon. So I have this gauche interaction between my CH2 and my CH3. Why would it stop with one of the other up carbons? If I could shift my Newman projection and look at a different carbon-carbon bond, I would actually find there's steric strain with both up carbons and the methyl group. So by being axial, it has at least two steric strains. Let's take a second to look at what would happen in the Newman projection of our of our equatorial methyl. You might do this by just keeping this Newman projection that you've just made and going to the other side and drawing your methyl in as an equatorial group. I'm going to redraw it. Methyl is now on my front carbon, and it's going up to the right. Hydrogen is down axial, connects to a up carbon to the other Newman projection. Back carbons connect by a down carbon. Hydrogens, hydrogens. Do I have torsional strain? No. No eclipse bonds. Do I have steric strain? What is the methyl gauche 2 now? Hydrogen and hydrogen. Is there steric strain? No, because hydrogens won't contribute to that steric strain. No gauche steric strains. No steric strain at all. Well, except for maybe the up carbon and the down carbon in the middle, but that's unavoidable. Not something that we're able to really fix. Or maybe I should say it's consistent in every chair. So what did this tell us? Axial groups experience a minimum of 2 steric strains, and equatorial groups experience a minimum of 0 steric strain. And of course, this is a mono-substituted ring. So I could start throwing in a bunch of other substituents, and I could make a much more complicated structure, but I will always have more steric strain with axial groups. So here's our rule of thumb. The higher energy chair has more axial groups. Period. That's it. You don't have to look for anything else. The higher chair, the higher energy chair, has more axial groups. So it is true that for methyl cyclohexane, the 2 chair conformations are not of equal energy. They are instead of different energies. One is more stable, one is higher energy. Can you tell me which conformation has the methyl group anti to a hydrogen? Let's call it chair A and chair B. Which chair, the higher energy or the lower, chair A or chair B, has the methyl group placed anti to a hydrogen? I can't really see it in the chair conformation, but the Newman projection shows me methyl is anti to a hydrogen. And here, when it's axial, here where it's equatorial, what's anti to it? Another carbon, a part of the ring, which is what we drew earlier when we said the bromines being anti would be the lowest energy. When those big groups are anti to each other, it's lower energy. And it'd be higher energy if they're eclipsed. Here, I'm anti to a hydrogen. I'd rather be anti to a larger group than anti to a smaller group. Okay, exciting stuff. So I gave you guys a worksheet. There are three things to consider here. 1, can you tell me whether this is a cis di-substituted ring or a trans di-substituted ring? This is trans. 1 group wedged, 1 group dashed. Now, it doesn't matter where you put them, but it does matter the relative placement of how you put them. The wedged group always needs to be related to the dashed group in this clockwise rotation. Wedged to dashed, clockwise. Up to down, clockwise. Notice that I've given you the first chair where they're both axial. Up to down is clockwise. We're going to get into this concept of chirality after this worksheet, and that is the cornerstone. The relationship that they have relative to each other has to stay consistent. So I want you to draw the other chair conformation, and then this is what we were talking about earlier. There's more than one way to draw that other chair conformation, more than one perspective. So all I want you to do is flip the chair and draw that new chair from two different perspectives. Recognize that you can look at it more than one way. Problem number 2, draw both chair conformations and decide for both of these which is highest energy. And then for number 3, you're given one chair conformation. I want you to be able to go backwards. From that chair, can you draw this top-down view? What is wedged? What is dashed? How are they oriented relative to each other? And draw the other chair conformation and decide what is highest and lowest energy. So 3 things: going between top, down, and chair, being able to go forward and backwards between these two different perspectives, flipping chairs, drawing one conformation, drawing the other conformation, and analyzing the energy, identifying the highest energy, the lowest energy. I'll write that down. Get started working with each other on solving this. I'll leave these tips up here about what happens to your groups. Yes. Yeah, absolutely.
And then one here. This one is going to say, so you could start anywhere on the chair.
Anywhere. But then, if you've got 2 groups or 3 or more, wherever you've started, your next group needs to be relative to that first group correctly. So it doesn't matter where you start, but it does matter how you continue. Is anybody interested in flipping the chair? Getting familiar with that chair flip?
Yeah, it can be either one, either axial or polar, but like it's always gonna be up.
Good.
It's gonna be always down.
Okay, so let's start here. We've got our first chair. How are those groups going to show up in our second chair? Good. Not a lot to guess there, right? But now let's consider that we rotate it a little bit. Right now you're looking at these groups kind of coming at you. Now let's rotate it and show how they look from a slightly different perspective.
yeah, that's how I'm feeling.
What group goes here? OH. Mm-hmm. Good. Is this a down OH group or an up OH group? Would you say that you're going towards the bottom of the page by following this line, or the top of the page? The bottom. So that means it's down.
I put, since this is a carbon that's pointing up.
Is this an equatorial group or an axial group? Good. How about this? Up or down? Because you'd reach the top of the page. Good. Equatorial or axial? Equatorial. Here's what it will look like if it's axial. It'll be straight up. If it's equatorial, it'll have this slant to it. It'll be slightly diagonal. Okay, how about this? Up or down?
And then this one, I'm just switching to an up.
Yep, it points towards the top of the page. Up or down? Good. Axial or equatorial? Axial. Here it's down equatorial. This group is this group. Down and down, up and up. But remember, axial groups, like this one, flip to become equatorial groups, like this one. So you'll get familiar with it. It's going to take practice. But those axial groups come straight up and straight down. Those equatorial groups are always pointed at weird little angles, right? Good. All right, now let's do it one more time.
It has to be equatorial.
Up or down?
Axial ones. Follow like
Mm-hmm. Down. Axial or equatorial? Does it point straight down or is it slightly at an angle? Equatorial. Good. Up or down? Oh, follow it from the chair. Is it going to go to the top of the page or the bottom of the page? I'm not sure. I think that's the top of your page, isn't it? Yeah. Up. Axial or equatorial?
We didn't talk about the axial.
Axial will be straight up and down. Is it straight up and down? Equatorial. So here's what I want you to mark. Axial equals straight up and down.
Well, I guess you choose, right? Yes, he's just letting us choose.
Equatorial. What's a good word for it? Slanted, angled, angled. Okay. Hey, hey.
Do this one.
Did you know that this yellow is not that yellow?
Wait, what is this one? Isn't it flipped?
No, it's rotated.
Oh. What's going on?
Up or down?
Down.
Up or down?
Up.
Right. It's up, then it's up, then it's up. It's catchy, right?
Going down to the depths of hell after I failed this class.
We're not gonna fail.
Yeah, I agree. You're not going to fail. Who can I help? Hey, Perla.
I'm confused.
Okay. Oh, you're drawing them yourself,
Yes.
huh? Do you want to download it?
I could.
Because this is on Canvas.
Oh, okay.
If you want to download it,
I could, yeah.
it's up to you. I don't want you to have to feel like you're confused because you don't know if you're drawing it right or not.
Okay.
Because you're not going to have to draw it for my class. It'll be under Unit 2. Let's close this guy. And it is chairs and absolute configurations. There you go. So this first one, it already gives you where your groups are going to be. And notice how this says they're equal. So it's saying these are not different from each other. They're just slightly rotated around.
Okay.
So here's an axial group. Good. Is it up or down?
Up.
Good. So it's going to be up in the other chair as well. Good. Notice how that bond points up towards the top of your page?
Yeah.
And this bond points down towards the bottom of your page. What about here? Where will the up group be? Good.
Yeah.
And down. This one points up. It's less steep up, but it's still up.
Okay.
Good.
So then would this be axial?
Axial is always straight up and down.
Okay.
Equatorial will always have these slight angles to them.
Okay. So equatorial.
Good. Up equatorial, in fact. And of course, the group that will be there is
The OH.
OH, because that's the only group. And what about here?
OH.
And how will we describe it? This one.
Would it be pointed down?
It is. Look how you'll end up at the bottom of the page. So it's down. Is it straight up and down, or is it angled? Yeah.
Okay.
So axial or equatorial?
Equatorial.
Good. Did that help? Yes. Good kickstart? Okay. And you can talk with these guys too about what they got. So Natalie, this one looks equatorial because it's at that slight angle, but it's an up group on an up carbon.
Oh.
So it should be up axial.
Oh, so it needs, if I just draw it flatter?
More, not,
like this.
More, oh, like
more up.
totally up.
Yes, straight up.
Sorry,
What you've actually drawn,
Here's when we were drawing them.
No,
what you've drawn looks up equatorial.
No, I understand.
Okay,
now.
good.
Yes, that makes sense.
Good.
I see.
Here it is up equatorial, it's perfect.
Yeah.
You kept that same angle, but it actually
I
should
did.
shift.
Yeah, that's
Same thing with this guy.
same thing.
Good.
Okay, I see.
But since this one's up, I could draw here.
How are you guys?
Stuck.
Okay. Oh, up stuck or like Cardi B stuck or?
Yeah, all of them.
Do you know what she was talking about? With a student told me she was talking about being constipated.
What?
I think I prefer that to be better, other than what it could be. Yeah.
When we're going here, both. Okay, so if we're like looking at it like this, the wedges are coming out, so you flip it, and then they're
Yeah,
up
they're
axial.
up or up equatorial.
It can go either way.
They should be up.
Doesn't matter if it's axial or equatorial,
It will be one in one conformation and the other in the other.
depending on if it lands on an up or down carbon.
Correct. Correct. So you drew your ethyl and you're like, it's up. I'm happy with that. But you were getting to your tert-butyl and you were going to say,
That's a down carbon,
so the up position is
so it has to be
up equatorial.
okay.
If it's up, so it really was stuck up.
So you did that?
So like,
Perfect.
because when you,
Now you randomly picked a carbon, and you randomly decided that ethyl should be on an up carbon.
Yeah.
Great.
Is that fine?
Now when you do the other chair, ethyl has to be on a,
Down carbon,
there you go.
Down.
And tert-butyl will be on a,
up carbon.
perfect. Prove it. Pick a down carbon on the next chair. And oh, where is the ethyl?
would they flip sides?
It doesn't matter where on the ring you pick. It matters its position. You've just drawn up.
No, it's equatorial.
Yes.
Take it.
You just drew up ethyl, down.
I'll redraw it.
Yeah.
So, how can you tell if something's axial or equatorial by?
From the top-down view, you can't.
Okay.
It is impossible. It's why we flip it on its side. And when you flip it on its side, you're going to end up finding it in two different conformations. So you have to draw both.
Oh, okay.
The top-down view is not one conformation or the other. The top-down view is a simplification.
Okay. So this ethyl is wedged, so it's coming towards us.
Good.
So it has to be on an up carbon.
No, it has to be up.
It has to be up. Okay.
And up carbons have up axial groups. And down carbons have up equatorial groups.
Up carbon has an up axial.
Yep.
Okay.
Down carbon has up equatorial. Yeah. Or one of this or one of those? Yeah.
So same thing. You just put the carbon
You bet.
down carbon has the up equatorial. Okay.
Every carbon has an up and down position.
Okay. Right.
So if it's an up group, doesn't matter what kind of carbon it's on, it just needs to go up. But it does matter how it shows up, literally. Thank you, I did not try that. Depending on whether it's an up carbon or a down carbon. So where is your tert-butyl? What carbon is it on?
Does that matter? Like, because this one's 3 carbons apart, so does that have to be 1, 2, 3 carbons apart?
Perfect, yep. They have to be 1, 4.
Right. So if I
This
started
is a
here.
wedge, so it has to be up. Since it's a down carbon, it's an up equatorial.
Nailed it. Oh, I just got goosebumps. Great job, Gabby. Hi, Camila.
Can you look?
Good question. Start by drawing the down axial.
Yeah, I would go like this.
Good. And now draw one that's perfect. There actually is a trick, which is that this line is diagonal to this line.
Oh, they're parallel.
They're parallel. That's what I meant. But it doesn't really matter. So you have not put your two groups with the correct carbon positions.
Oh, because I didn't count right, huh?
Yeah, you did 1, 2, 3, 4.
And it's supposed to be over
You did
here.
1, 4.
How about this one?
Up, 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 up. Great.
Really?
Yes. And
Bad.
here, I think the problem is you had up carbon to up carbon, down carbon to down carbon. So you didn't actually flip anything.
Oh.
In fact, the only thing you did was you moved the chlorine to a different position,
Yeah.
but then you actually drew the groups on that position wrong. This is a down carbon, so it has a down axial group and an up equatorial, but you drew it as if it had up axial and down equatorial. So, yeah, get these. Good, good.
Thank you.
You bet. Annie, how are you?
I'm also because I didn't realize that down carbons.
Okay. Makes sense now?
Yeah, because I was like, I guess I'll start here.
Okay.
Okay, I think I'm wrong, by the way, but can you draw it like this?
You have actually changed the orientation of all of the groups.
So no?
You have drawn its mirror image molecule, which is a different molecule.
Okay.
So you notice how your aldehyde to ether is clockwise. And now your aldehyde to ether is counterclockwise. You drew it wrong.
Okay.
And you haven't flipped any of the carbons.
Okay.
Oh, actually, no, I'm sorry, you have.
I have.
You
but
did.
you just can't do that.
So you drew the lower energy conformation of its enantiomer.
Okay, got it.
Yep.
Okay.
How are you guys?
I think we're good. Do you want to tell us if we're actually good?
Yeah, I do. Looks great.
Okay.
Good job.
I'm throwing my
I
Newman
don't
upside
like
down.
this.
You just do it. I don't have any other words for you.
I would like it from this perspective. So you're doing it down, two carbons, like two carbons. I got
All right, some of the answers are on the board. Never got to you guys. How you feeling? Oh no.
Okay, we got a question.
Yeah. This is great.
Okay.
You arbitrarily, looks like you put ethyl on an up carbon.
Yeah, we were going to ask you about that.
That's great.
What is the up and what's the bottom? I don't.
Well, so this is a wedged group, so it's up towards us. And you picked for it to be on an up carbon. Up carbons have two positions, up axial and down equatorial. So since I need ethyl to be up, it has to go up axial. Now because you picked ethyl to go here, tert-butyl has to go here. Tert-butyl is also up, but this is not an up carbon.
Yeah, that's what was.
Every carbon has two positions. A down carbon has down axial, up equatorial. Tert-butyl has to be up, so it will be up equatorial.
Okay.
Now that's just one option because you randomly chose for ethyl to be on an up carbon.
Yeah.
Let's draw the other option where ethyl is on a down carbon.
So you did like
Will it still be axial?
No, equatorial.
Because when groups swap, when they flip through a chair flip, they'll become equatorial groups.
So it does matter, like if it's like down carbon has to be equatorial, not like an axial carbon, not an axial.
Yes.
Okay.
So up group, up group, up group.
Yeah, I thought it didn't matter. Like I could
whether
potentially
it's-
choose for it to be down. Actually.
No,
So why is this one on a down then? and this
it's
one's
on a down carbon, but it is
Okay.
an up group on that down carbon.
Okay, that makes sense.
So ethyl became an up equatorial. What happens to tert butyl? By the way, here's position 1, so position 4 is going to be back here. Is tert butyl still on a down carbon?
No.
Now it's on an up carbon. What's the up position?
Axial.
So tert butyl flipped from equatorial to axial. Ethyl flipped from axial to equatorial because they flipped carbons.
Okay, that makes sense.
Good. And which one is higher energy? Which one has equatorial? Perfect. Close. This one looks great. This one I think should be straight up and down. Yep. Just like how this is straight up and down, this one becomes straight up and down. Great job. Perfect. Perfect. You nailed it. Way to go, Lean. We're not going to do that little part on the bottom. That was basically the activity that we did Monday and last week. Okay, feeling better? Understanding your perspectives a little bit more? This is good, by the way. Great.
I accidentally wrote that.
That's good. Okay. So in my cis 1 tert butyl 4 ethyl, you can't name all of these necessarily, but you could definitely name this second compound. In cis 1 ethyl 4 tert butyl, I have 2 conformations. One where ethyl is axial and tert butyl is equatorial, and one where tert butyl is axial and ethyl is equatorial. So I have 1 axial group. Oh my goodness. And I have 1 axial group. So which one is higher energy? The one with the more axial groups, right? That's what we decided earlier by looking at Newman projections. So they're equal? No. Now we can look at which group is larger in the axial position. Because larger group, larger strain. So does ethyl create more strain being axial, or does tert butyl? Why? More atoms. It's a bigger group. Bigger strain. So they do have the same number of groups, but the groups are not identical. What about the first one, by the way? The trans diol. When they're both axial or when they're both equatorial, what's higher energy?
Axial.
Both axial is higher energy. Here, it's when tert butyl is axial that we have higher energy. All right, now we've got this tri-substituted ring. What's higher energy? The ring on the left that you were given, or the ring on the right? Why? 2 axial groups. It's a weird 2. Here I have only 1 axial group. So this is higher energy. I'm going to be honest, I don't really want to take a break, but I know that it's good for you. So let's take a short 5-minute break. Camilla? Feel free to get up, get your blood flowing, move around for a little bit. Yes. Well, it has to. It's given to you, so you don't have to guess.
I know, but it doesn't make sense.
These are the same chair.
Okay.
These are different chairs. Which is why we're showing equilibrium. There's some energy needed to flip between chairs.
Okay.
But here I just showed an equal sign.
Like a different position.
Yeah.
Okay.
Yeah.
Okay.
So what I wanted to show you there was you could take this molecule and just rotate it.
And it would be in a different. Yeah.
I've got down equatorial on this like center front carbon. And now I've rotated it so that down equatorial is on this back right carbon.
So when looking, these three are down, these three are tops.
No.
I know, that's why I was like, the only.
No, that's a good point, actually.
Down.
Yes. Oh, no, sorry. Up, up, up. The 3 you just circled were all up.
All up, yes.
Yeah.
Okay. No, I'm trying to-
Now here's a way that I literally mean that it's up. Look at this OH group and the bond that it has coming from the ring. Which way does it point? Up.
Yeah.
Now what about this one? Which way does it point?
Down.
And it's like really slanted down.
Yeah.
This one is like barely up,
Barely up.
but it is up. Okay, the same thing with the carbons. Look at this vertex that this carbon forms.
Yeah.
Which way does that vertex point?
Up.
Which way does this vertex point? So that's one way that we can actually identify up carbons and down carbons. How does the vertex point to it? And remember that this is a 2-dimensional drawing of a 3-dimensional object drawn mostly on its side. So there's something we can add if I can borrow your pen. We can actually bold these lines. And now it looks like this is closer to us
Okay, yeah.
and this is further away. It's not always helpful, but it's sometimes helpful.
So on this one, it would be up axial, up axial, up axial.
Good.
Equatorial, and then up equatorial, up equatorial, equatorial,
Beautiful.
down axial. Okay. I might just like write it down.
Good.
Stare at.
Practice it. Repeat it. Mm-hmm.
The homework is due tonight. I'm like missing a rule or something. I don't know. Is this not
Oh, yeah, but I is alphabetical before M.
Okay, I think I put that before in it. So, does it matter if this
Oh,
is
it also wants the stereochemistry. So it wants you to describe it as a cis disubstituted ring or a trans disubstituted ring. Like that up there is cis 1-tert-butyl 4-ethyl cyclohexane, not trans 1-tert-butyl 4-ethyl cyclohexane. So what's the relationship between these two groups? Are they cis or are they trans? Why is this one up here cis?
because they're both coming the same direction?
Good. They're both wedged. They're both up.
Yes.
Both up?
No, this one would be down. Yeah, that's down.
So cis or trans?
Trans.
There you go.
And that would go before.
It does go in the front. Yep.
So, and then ISO. You do count the ISO in alphabetical sometimes.
Yes. Yes.
Yeah, we're just old. We're getting old. That's what it means.
Now I decided how I changed the way I teach Unit 3 because I heard from another professor it's better to put the hardest material at the front so that you have more time to master it before the unit test. Now I'm starting to think maybe I should put chair conformations ahead of nomenclature. Yeah, I don't need you to be able to name that ring, to have you understand its stereochemistry. But it is useful because then I can just say, draw the chair conformations of cis 1-tert-butyl 4-ethyl cyclohexane. But technically we could do that later, and nomenclature is not hard, it's just tedious. There's a lot of little rules, but you practice them enough, it's easy enough to overcome. It's annoying, but it's not like it's impossible. This can feel impossible. I saw a ton of light bulbs click today. I loved seeing that. That's what we call active learning. I mean, I talked and talked, but until you did it, those light bulbs didn't go on. And the nomenclature stuff, I think maybe maybe it should come after stereochemistry. But then how do I tell you to go do a pre-reading? Because it's going to be giving you all this name. I don't know. Maybe I should just write my own textbook. Please, if I wrote a textbook, it would be open education resource. It would be free.
There's a professor that wrote his own textbook, but half of it was like redacted.
Redacted because it had like privileged knowledge, like
Maybe he was like
intellectual merit.
anymore, so I'm just gonna redact it.
Redact, you should do like a cross through, you know, like strike out the words, don't redact it.
I was like, what are we learning?
That's so silly. Yes.
On that problem, when you're numbering it, do you number alphabetically too if you can?
No.
Because,
Lowest locant set.
right, so you have 1 and 4.
Why? It's going to be 1 and 4 no matter which way I start from and go.
Yeah, but she put trans 4.
But that's because you could have gone either way. It was a tie. It's 1-4 or 1-4. In the case of a tie, we name alphabetically. Only in the case of a tie do we number it alphabetically. So you could have 1 isopropyl 4-methyl or 4 isopropyl 1-methyl, 1-4 or 1-4, same locant set. So how do you pick which locant set? Give the lowest alphabetically.
Okay, so isopropyl doesn't.
It's the same thing here, actually. Because they're 1-4, I will give tert-butyl position 1 just because it comes first alphabetically. Not because naming ethyl at 1 is a lower locant set or a higher locant set, but just because it's a tied locant set, and the tie always goes alphabetically. Same thing, Jude's not here today, but he brought this up the other day. He thought we prioritize halogens, give the halogen its lowest locant set. Not true. We prioritize the lowest locant set when it's alkyl groups and halogens. And if it's a tie, we go alphabetically, and that's usually going to be a halogen, because you've got bromo, chloro, and those often come before ethyl and iodo and methyl, isopropyl. Anyways, good?
Yeah, thank you.
Okay, you're welcome. All right, I need you guys to take some molecules. So okay, good catch. Yeah. Molecules in motion, am I right? How many more we got in the classroom? You guys ever put your right hand on your left foot? No, sorry. Your right shoe on your left foot?
Maybe when I was a kid.
Crazy. Why would you do that? Can't you tell the difference between your right foot and your left shoe? Is it not? How often do you do that? Never. Maybe when you were 2, because you don't really care about how uncomfortable it feels when you're putting your left shoe on your right foot, but there is something wrong with it. We call that chirality. There is a synonym for chirality. Its name is asymmetry. Chirality is asymmetry. Can you imagine the guy, could have been a girl, could have been a person. It was definitely a person. Can you imagine the person that said, asymmetry is so relevant to me that I'm going to give it its own word? Do you know what the synonym for symmetric is? Achiral. Depends on what perspective you want to look at a structure from. Do you want to look at it for its symmetry or lack of symmetry? Or do you want to look at it for its lack of symmetry or its lack of symmetry? That's what achiral means. Lacking the lack of symmetry, having symmetry. Not having symmetry. Why would you do that? Well, let's talk about what chiral means. Chiral is Greek. Nope, Latin. And it means handedness. Kind of like your foot, your hands are mirror images of each other. Although a lot of gloves, it doesn't actually matter which hand you put it on because your gloves can fit. But with shoes, often you can really tell the difference between your left shoe and your right shoe. Sometimes gloves, you can tell the difference between your right glove and your left glove. But your hands are mirror images, but they lack symmetry. So chirality is this idea of lacking symmetry, and especially how that relates to the mirror image of that asymmetric object. Your hands cannot superimpose. They are identical in every way, except they are completely different. Exact opposites. You agree? What hand do I have up here? Sorry? My left hand? Why? Oh, because you saw me do it. How stupid do you feel now? What hand do I have up here? I don't have either hand. That is not my left hand. That is not my right hand. Because that hand is achiral. Chirality means handedness. This does not have handedness. Because the front of this hand that you see is identical to the back of the hand that you can't see because you have to look at it from the other side of the board. It has a plane of symmetry that is the atom's thick line of ink that I have drawn on the board. Okay, well, now let me add these. Now which hand is it? Now it's my left hand. It has to be my left hand because I can't get my fingernails to superimpose with that. Right? Here's an example of chirality in molecules, handedness of molecules. These two molecules, sorry, I'm going to have to throw them at you guys again. These two molecules are perfect mirror images of each other. Here, let me flip the mirror image around. Here, let me show the mirror image this way. Let me show the mirror image this way. These are perfect mirror images, and yet, sorry, got to make sure the zigzags stay the same. When I try to get those yellow groups to line up with each other, one goes forward and one goes backwards. They don't line up, which is kind of like your hands. Your fingernails point in opposite directions when you get your fingers to line up. When I get my carbon chain to line up, the groups point in opposite directions. That is literally handedness. Well, let me try to get the groups to line up with each other. Okay, now they're pointing in the same direction, but do you notice my carbon chains don't line up? Which is very similar to when I try to point. I'll point my fingernails in the same direction, but now my fingers don't all line up. These molecules are chiral. They lack symmetry, which makes them non-superimposable with their mirror image. That's the basis of what we're going to talk about here. Okay? First thing to discuss with chirality in molecules are chiral carbons. Did I give you guys the worksheet? No, of course not. Why would I use my break to give you the worksheet? Chiral molecules. You'll notice on this worksheet that I've drawn like a tetrahedral center, and I've related it. Let's just pass a bunch down. I've related it to a couple of other tetrahedral centers by means of these mirrors. So these mirrors show how these groups are symmetric to each other. Oh, good, it's just enough. Everybody got one? Did you guys get one? Good. A chiral carbon, well, that is an asymmetric carbon, also called a chirality center. It lacks symmetry. Yeah. I just uploaded it, but I didn't put it in the right spot. It's now above descriptors and relationships on Unit 2. It's right. It is. I just uploaded it. Yep. In order to lack symmetry, here's what a chiral carbon needs. It will have 4 distinct groups. For instance, with my little yellow molecules, here's a chiral carbon. The 4 distinct groups are hydrogen, methyl, ethyl, and whatever this is, SH, sulfide. Notice how this is not 4 distinct atoms. I've got 2 carbons that are connected to my chiral carbon. It's not having 4 distinct atoms attached, 4 distinct elements. It's 4 distinct groups. And here, a methyl is distinct from an ethyl group. Those are not the same. A 1-carbon chain is not symmetric to a 2-carbon chain. So we need to have 4 distinct groups. I want you guys to go through these molecules and identify carbons that have 4 distinct groups. I'll give you a hint. sp2 hybridized carbons, trigonal planar carbons, carbons in double bonds, only have 3 groups. So sp2 carbons are never chiral centers. You're going to be looking at tetrahedral carbons, sp3. Go through and find as many chiral carbons as you can in all of these molecules. By the way, some of these are your molecules. Thank you. I never know what molecules to give, so I just go through your submissions and I pick them. Oh, I didn't put the names on the first 3. That is acetaminophen, ibuprofen, and threonine, which is an amino acid. I should have put those names on there, but I forgot. So those are very relevant molecules to our world. Acetaminophen, ibuprofen, threonine.
Did somebody choose fentanyl?
Yes. I don't remember who. It was in the first half of the class because I only went through the first half to get my samples before I came in today. How many chiral carbons?
I don't know. How to know?
Let's start by looking at carbons that have 4 groups.
What do you mean by 4 groups?
All of these carbons in the ring, do they have 4 groups?
No.
Right. They're sp2, they only have 3 groups. How about this carbon in the carbonyl of the amide? Does that have 4 groups? CO double bond carbon?
No.
No, only has 3 groups. Okay, so there's only 1 carbon that has 4 groups. It's the CH3. Does it have 4 distinct groups?
No.
Remember, it's an end,
Okay.
so it's a carbon. There must be 3 hydrogens there.
Okay.
Does it have 4 distinct groups?
No.
No, it has 3 hydrogens. Those are all the same group. So acetaminophen has how many chiral carbons? 0. How about ibuprofen? Did you catch that, Mean? Do you want to listen in? These carbons are all sp2.
Like
0 chiral carbons because they only have 3 groups. And this has to have 4 distinct groups. This carbon here, also sp2, only 3 groups, cannot be chiral. This carbon has 4 groups, 3 hydrogens, and then the bond to this group. But are those 4 distinct groups? No, 3 of them are the same group, 3 hydrogens. No chiral carbons, write that above it, 0 chiral carbons.
So ibuprofen 0 too? Like 0?
Ibuprofen does not have 0. Now, I will say all 4 groups are not explicitly shown. Some are assumed.
Yes, but it only has 3 bonding areas.
Is it this one? That one's got 1. Which one? This one. It's gonna have a hydrogen.
Yep, hydrogen, the ring,
It's gonna have a CH3.
good,
And a CO double bond.
good. So it's got a carboxylic acid, a methyl, a hydrogen in the ring. Yep. Lean, why don't you turn around like Christine maybe, sorry, and work with them, walk through with them, and Perla, maybe the same for you with Natalie and Britton. This is the only carbon that has 4 groups. Does it have 4 distinct groups?
Oh. So all of them have to be different or just some?
Absolutely.
So there are 4 different.
4 distinct groups.
So there can't be 2 that are the same.
If any 2 are the same, it's an achiral carbon.
Whoops.
Oh, so we got like a lot of them wrong.
That's right.
Okay.
Got it. Oh, sorry.
That's okay. So you identified all of the tetrahedral carbons,
Yes.
which is a great start because the chiral carbons will be tetrahedral carbons.
True.
Okay.
Okay. I'm just gonna color it. So.
Perla, you're actually on an old document.
Oh.
So I did upload this to Canvas, but literally just
Okay.
now.
So if it's distinct
So
group-
under Unit 2, it's now chirality. Where is chirality? You know what? You might need to reload.
Okay, this one would be.
Sorry about that.
None.
0,
Okay.
1, 2. Great job. Keep going. All of them. Good.
This one we're.
Good, 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 good.
Those are all good.
All achiral.
Okay.
But this carbon here, I'm going to point on Gabby's, is chiral. Hydrogen, methyl, carboxylic acid, aromatic ring.
So it can be bonded to carbon. The carbon just has to be bonded to other things.
Yes. Like my example up there, one side was a methyl, one side was an ethyl. Those are distinct groups despite being all 4 carbons.
So then this one would also be chiral.
No, only 3 groups.
Oh, double bond.
Good, good. Okay, keep going through the rest of them. Oh, and there's a second one here on this molecule.
Is there not a chiral?
Yes.
Okay.
Yes.
I don't know how to pronounce it.
Chiral,
Chiral.
chi.
And then this would be one.
That's a chiral center.
H, and then you have this, and then you have this, and then you have this.
Perfect.
You're right.
And how many in 3 and 9?
3 and
Oh, there's more than one?
Yep.
Am I crazy?
Yep. Maybe.
Oh, maybe.
Yes. Now teach her. And then go do all the other ones below it. Do all of them. What do you got?
I'm doing phenol with this cannot because it would have a hydrogen sticking off.
Good question. No,
No.
because I can split that ring in half.
Oh.
From this carbon, I could go in either direction down the ring, and I meet back up at the other carbon or the other nitrogen.
Would this one be since?
Yes.
Okay. Okay.
Yes.
That was gonna be my next question. Like, do I avoid rings altogether? No. But it's just like if it's a symmetrical ring that
Yes.
either side. I mean, technically this is symmetrical too, but it's gonna divide in the middle of the bond.
It's not symmetric because if you do cut this, I've got methyl on one half and I've got this whole other steroid structure on the other half.
Okay. Okay, that's a good point.
So there actually is no
So the
symmetry through
reason
this.
Here, like if this nitrogen was right there, then it would be
then it would be chiral.
Okay.
Now tell them all that again.
I need hours of.
Good, now do all of these.
Oh, okay.
All right. We got to hustle. Ready? Acetaminophen, 0. Ibuprofen, 1. Threonine, 2. Dexamethasone, like 1 billion.
Can you show us how to count those in the ring? Because
Yes.
you like look at one and go like, it's like the same.
You keep going until there's a point of difference, and if there's no point of difference, then they're different. Or sorry, you keep going until a point of difference. If there is no difference, then they're the same group, and it's achiral. All right, where is it? Chirality. Let's look at dexamethasone first. With dexamethasone, none of the sp2 carbons are chiral because they only have 3 groups. But this carbon in the ring, man almighty. This carbon in the ring that has a methyl group and then 3 very distinct bonds in the ring, chiral, 4 distinct groups. The carbon bonded to fluorine, it has 3 very distinct bonds in the ring. They're going to very different parts of different rings, chiral. All right, here's a fun one. CH2, achiral. It has 2 hydrogens. CH2, achiral. CH and 3 very different parts of different rings, chiral. This carbon in the ring, right where it kind of makes this swoosh up, chiral carbon. The CH group is chiral. Okay, then the carbon bonded to alcohol, chiral. CH2, achiral. Another CH2 down on this bottom ring. How about the CH next to it? Chiral. 4 distinct groups. The hydrogen, the ring to the right, the ring to the top, the ring to the left, all distinct groups. The carbon with the methyl, chiral. The carbon with the alcohol and the carbonyl, chiral. How about the CH2OH? Achiral. Kirsten.
Going back to the beginning of that, on the farthest left ring,
Yeah.
I guess the question that I have is the reason why that furthest left, like 4-way split is chiral, is that
Because the ring to the top is a CH, and the ring to the bottom is a C.
Oh, okay.
Different groups.
Okay.
Okay, what about fentanyl? A lot of people will look at this carbon in the ring of fentanyl and think, well, it's a tetrahedral carbon, it's got a lot going on with it, but it is achiral, and that's because this ring goes CH2 left and right, which connects to CH2 on both the left and right, and then connects back together at the nitrogen. Despite the fact that the nitrogen has 2 different groups, and then the other nitrogen has a very distinct group, this carbon, which is, I suspect, the only one you even looked at, because all of the others are CH2. Hi, Eric, come on in. All of the other carbons are CH2s, achiral. But this CH carbon, we looked at other carbons in dexamethasone that were CH groups and were chiral. This CH group is achiral because the ring is symmetric to itself. CH2, CH2N, CH2, CH2N. Achiral. Isn't it beautiful? All right, let's move on to absolute configuration. This essentially comes to answer the question, is it my left hand or is it my right hand? A very cool, you get why we call it absolute configuration, yeah? It's absolutely my left hand or it's absolutely my right hand. It's absolutely this orientation in space or it's absolutely that. It's not one or the other. A very cool example of this is this molecule. Do any of you know it? Yeah. It's methamphetamine. Highly addictive in one configuration. How many chiral carbons in methamphetamine? This right under absolute configurations. How many chiral carbons? Just one. It's the carbon that connects to the nitrogen, to the amine. Methyl, a benzene ring, a hydrogen, and the amine. 4 distinct groups. So that means that chiral carbon can either have the amine group wedged or dashed. Those are the 2 configurations that are different from each other, that are mirror images. Do you know what my activity was with this? And I'm going to run out of time again. I was going to have you guys find your matching compounds like this and decide if you're the same or different and what the relationship is. We might run out of time. And I did in the fall too. Okay, here's the deal. Vicks Vapor Rub. You guys use Vicks Vapor Rub? Do you know what it does? Opens the nasal passages, helps you breathe better. This is the active ingredient in Vicks Vapor Rub. Crystal meth, highly addictive, amphetamine. Imagine driving with your right hand and getting to work safely, and driving with your left hand and driving upside down the entire way underwater. That's the distinction that those 2 molecules have from each other. Life or death, literally. Isn't that crazy? The way it takes up space will interact with your body because your body is also chiral. So imagine fitting the right hand into a nuclear reactor and shutting it off, and your left hand fits into the nuclear reactor to detonate it. Turn it off, I mean like shut it down. Detonate or turn it off. Difference is just the chirality, just the configuration. We use 2 terms to represent absolute configuration, R and S. R is Latin for righteous, no. Rotorus, it means right. And S is Latin for sinister, which means left or bad or evil. This is actually true of a lot of human cultures. Left-handed people used to be physically abused for writing with their left hand in the United States because it was seen as bad. In some Arab cultures, they don't eat with their left hand because it's dirty. They eat with the right hand. So there are these distinctions, but all we're using it here for is clockwise or counterclockwise. R is this clockwise rotation, which is why I've given this arrow in the top of the R. R is clockwise. S we'll use to represent things that are counterclockwise. So here's where this will come down to. If I want you to know your right hand from your left, then I will say, look at the rotation from pinky to thumb, and if pinky to thumb is clockwise, then it's your right hand. Pinky to thumb, right hand. Oh, but wait, here's my left hand, pinky to thumb, also clockwise. It's not good enough. So we have to establish a reference point. With your palm facing forward, Well, sorry, I guess it's going to be confusing the way you look at it, right? When looking at your palm, pinky to thumb clockwise is right. When looking at your palm, pinky to thumb counterclockwise is left. Do you agree? By establishing a point of reference and an order, we can distinguish between two mirror images that are different from each other. Establish a point of order, then recognize the rotation. So here's what we're going to do. These are called the Kahn-Ingold Prelog rules. Rule number 1, assign priority, so that means 1 to 4, by highest atomic mass. Of course, at the first point of difference. If two of your groups are both carbons, that's not different. So then you have to go further to the next atom in that group. Now you've got hydrogen against carbon. Oh, okay, carbon is higher. That's a higher group. You consider a group all the way in its own. Do you add up the masses of the groups? No. You go atom by atom down a group until you find an atom that has a higher atomic mass. Rule number 2, place priority number 4, that is the lowest atomic mass, backwards. What do I mean by backwards? I mean away, which means we'll draw this as a dash. Priority number 4 is backwards, away from you. That's, like I said, looking at your palm. That's the reference point. First, we need to identify what is pinky and thumb, groups 1 to 4. Now we need to establish a reference, put number 4 away from you, and now we determine rotation just between 1, 2, and 3. 1 to 2 to 3. Ignore priority 4. We already know where priority 4 is. It's back. Okay, so let's do this for methamphetamine. Let's take the structure on the left. And let's look at the chiral carbon and assign priority 1 to 2 to 3 to 4. Highest and lowest priority are often the easiest to assign. What is the highest priority group attached to my carbon, Eric? Why?
Because it has the highest atomic mass compared to hydrogen and the 2 carbons.
Nitrogen is a higher atomic mass than carbon or hydrogen. Relative to my chiral carbon, that's our center point, nitrogen is the highest atomic mass. What is my priority number 4? Hydrogen. And it's already going away. It's already dashed. Now, how do I decide between priority 2 and 3? What I have here is a carbon, and what I have here is a carbon. So we can list out the atoms that they are bonded to. First of all, we'll just look past those groups because we already know what they came from. This is bonded to 3 hydrogens, but this is bonded to a carbon and 2 hydrogens. Carbon and carbon are not different. The point of difference is comparing carbon to hydrogen further down the chain. I'm actually comparing this carbon to this hydrogen. Yeah? So what's higher, carbon or hydrogen? Carbon. Not at the first point from the chiral carbon, but at the second point in the chain from the chiral carbon. Keep moving out until you reach a difference. And if you don't reach a difference, it's not a chiral carbon. That would be two identical groups. So here's priority number 3. Here's priority number, here's priority number 2 on the left. Priority number 3 on the right. Assign priority 1 to 2 to 3. Place the lowest priority back. Conveniently, it's already back. If you need to, you could rotate it into a new conformation. You could flip your molecule over. Then determine rotation 1 to 2 to 3. Here's 1. I'm ignoring 4. I'm not paying attention to 4. Here's 1. Here's 2. Here's 3. What direction is that? Clockwise. This configuration is R. Here's a fun little trick about absolute configurations. Swap the placement of any two groups. Swap the configuration. If you want to show the enantiomer, all you have to do is break two groups off and swap how they're bonded. Okay, physically, you don't do that. You don't take a molecule and break the bonds apart and swap them. This is a mental game, or a drawing game. If you can swap the placement of any two groups, then you can swap the configuration. You guys saw earlier how these were two different molecules, and now they're the same molecule. It's because I swapped two groups. I'll do it again. I'll make them different molecules. I'll swap the placement of the ethyl and the methyl groups, and now they become non-superimposable again. Mirror images that are non-superimposable. Brilliant. All right, so that means that by looking at the other form of methamphetamine, what are we looking at? Not R-methamphetamine, S-methamphetamine. But here's the problem with that drawing of S-methamphetamine. Priority number 4 is coming towards you. It's not going back. But do you know how you could make it look like it's coming towards you? How you could make it look like it's going away from you? You could go into the hallway and look at my board from the hallway. Okay, let me say this a different way. What directions do the hands of a clock move relative to the numbers on the clock? The numbers. The letter, the numbers. I always say it wrong, and then I thought I said it wrong. The numbers look at the hands moving and say they are moving counterclockwise. Put yourself at number 12. Look at the hands in front of you. Which way are they moving? They're moving counterclockwise. Okay, let me do this. I'm going to show you rotation clockwise. Does this look clockwise? Without changing how I rotate, I'm just going to spin around. What way am I rotating? You just said I was rotating clockwise. Perspective is the important thing. Palm forward or palm backwards? Priority 4 forward or priority 4 backwards? So here's my tip. If priority 4 is coming towards you, notice how that's a wedge? Assign opposite of how it rotates. Assign opposite of how it appears. Okay, here's 1 to 2 to 3. Dang, that's the exact same rotation I had last time, but I know that these are different molecules. These are related as enantiomers. Wow. That means that I'm looking at it wrong, because priority number 4 is coming towards you. So, since priority 4 is coming towards you, it looks like it's R. It's actually S. You're just looking at it backwards. Go behind the board and look at it. Now you're looking at it right. So fun, right? Okay, I had problems for you to exercise there. Okay, here's what I'm worried about. I want to tell you that there are 3 classes of molecules: chiral, meso, and achiral. And I want to tell you that there are 2 types of relationships that molecules have with one another. They are diastereomers, or they are enantiomers, or they are the same. And I can't tell you all of that in 60 seconds. So would you rather that I assign you a lecture recording from my fall semester, in addition to me posting a video where I kind of continue my lecture and finish this worksheet, so that you can still take your unit test this weekend? And it's a long weekend, you have until Tuesday to do it. Or would you rather we wait until Wednesday to finish this lecture and take the unit test next weekend, followed by another unit test the weekend after, followed by the midterm the week after that?
Strike a hard bargain.
What do you recommend?
I think we should keep our pace. I want you guys to have a break next weekend. I want you to have some time between unit tests and then the midterm. I don't want to beat you so many times in a row with assignments like that. So I'm gonna send an announcement. I'm gonna link the recordings that I want you guys to watch from my fall and my summer lectures. I'm gonna upload a video where I finish this worksheet. And I'm gonna ask that you guys take the unit test this weekend. We've covered so much that there's just so little left. And I don't want to cut out the time from Unit 3, because you're going to be making the same faces you are right now in Unit 3, but for very different reasons. Yeah. So we're going to keep our unit test this weekend. You have a long weekend, so if you can, plan for the unit test to be Monday or Tuesday. Use our Monday lecture period. Happy President's Day. Have a good weekend, everybody. Thank you for your time.